So, let's talk about something truly huge. We're not just upgrading the internet. We are talking about completely rebuilding it from the ground up, using the fundamental, and let's be honest, seriously weird rules of the universe. And I mean physically impossible. Not just difficult, not just heavily encrypted, but protected by the actual laws of physics. A message where if someone even tries to peek at it, it instantly changes and you know you've got a spy. It sounds like something straight out of a movie, right? Well, it's not science fiction. Right now, all over the planet, brilliant teams are in a flat-out race to build that exact thing, a quantum internet. And what they're accomplishing is it's mind-blowing. But to get here, they had to solve a problem that for the longest time seemed absolutely fundamentally impossible. Okay, so what's the big deal? Why is this so ridiculously hard? I mean, we fiber optics that wrap the entire globe. Why can't we just shoot some quantum data down those same pipes? Well, here's where it gets crazy. A normal email can zap across a continent in less time than it takes you to blink. But if you try to send one quantum bit, just a single photon, down that exact same fiber optic cable, you'd be waiting for centuries. I'm not kidding. The signal just poof, it disappears. Over any real distance, it's completely useless. So what is going on here? You know, with our regular internet, we figured out how to deal with signals fading more than 100 years ago. So why can't we just do what we've always done? The solution has always been pretty straightforward. Repeaters. Back in the telegraph days, a signal would get weak, and a repeater would basically listen to the message and then shout a fresh, loud copy of it down the line. We do the exact same thing today. Your data screams through fiber optics, and every few miles an amplifier just reads the signal, makes a perfect copy, and sends a boosted version on its way. But that's the key. You have to read and copy the signal. And in the quantum world, that simple act is a total deal breaker. And this brings us to one of the most fundamental and frankly weirdest rules in all of physics, a rule that makes our old trick of just copying the signal totally, utterly impossible. It's called the no-cloning theorem, and it means exactly what it sounds like. The universe has basically disabled the copy-paste function for quantum information. You just can't look at a quantum particle, like a photon, and make a perfect clone of it. The very act of looking at it, of measuring it, changes it forever. Now, this is what makes quantum communication unhackable, but it's also our single biggest engineering nightmare. And this isn't just some clever idea, it's a proven law of nature. It's as real as gravity. You can't just engineer your way around it. The universe itself puts up a giant stop sign that says, nope, you cannot copy that. This is the question, isn't it? If you can't amplify the signal to get it from point A to point B, how in the world do you build a global network? For years, this looked like a total dead end. But here's the beautiful part. The same strange quantum rulebook that creates this problem also gives us an incredibly elegant and bizarre way around it. So to get around this no cloning rule, scientists had to embrace one of the most mysterious concepts in all of science, something so strange that it really bothered even Albert Einstein himself. Get ready for quantum entanglement. This is where things get really cool. You can link two particles together so that they basically become a single system. And if you measure one of them, you instantly know the state of the other one, even if it's on the other side of the galaxy. It's like they had this invisible, unbreakable connection. Einstein famously hated this idea. He called it spooky action at a distance because he thought it was just too weird to be true. But he was wrong. It is real. And this spooky link is the secret key we need to build the quantum internet. It lets us create a connection without ever having to send the actual information through the middle. So how do we actually use this spooky link to build a network? Well, we need a whole new kind of device. It's not an amplifier that copies data. It's more like a teleporter for the connection itself. And this is the giant leap in thinking. These new devices, called quantum repeaters, don't boost a signal that's fading. They don't pass a message along. Instead, they build this continuous, spooky connection from start to finish, one little piece at a time. They essentially teleport the entanglement. Okay, so think of it like a relay race for entanglement. The first repeater creates a short little entangled link with its neighbor, and then just holds onto it in a memory. Then that neighbor does the exact same thing with the next one in line, and so on. Once you have this whole chain of short, stable links, the repeaters do this wild trick called entanglement swapping. They basically stitch all those short links together, erasing the middlemen, and creating one single, unbroken, entangled connection between you and your friend hundreds of miles away. So for decades, this has been the idea. It's a beautiful theory. But building one in the real world? Incredibly hard. You see, you need a single device that can do three extremely difficult things, all at the same time. So to build one of these repeaters, your device has to be a triple threat. First, it has to be like a perfect catcher's mitt for a single, fleeting photon. Second, it needs a memory that's stable enough to hold on to that incredibly fragile quantum state. And third, it needs to have the processing power to actually perform that entanglement swap. And for the longest time, this was the roadblock. Researchers could build a device that was good at one of these things, or maybe even two. But a single, integrated device that could do all three, that was the missing link. It was the holy grail of quantum networking. And then, they did it! A team from Harvard and MIT built the world's first working prototype, and they did it using a tiny, perfectly engineered flaw inside a diamond, what's called a silicon vacancy center, that acts like a perfect little quantum trap. It can catch a photon, it can store its quantum state, and it can process it. This was the moment that proved a quantum repeater wasn't just a dream on a whiteboard, it was buildable. Okay, but that brings up another huge question. That whole relay race idea only works if you can hold on to the quantum information long enough to build the entire chain. For a long time, these quantum memories could only hold a state for tiny fractions of a second, not nearly good enough. But recent advances have completely changed the game. No, that is not a typo. Researchers have now built a quantum memory that can hold on to its state, its quantum purity, for over an hour. This is an absolutely mind-shattering leap forward. We're talking orders of magnitude better than what we had before. And this is the actual data. This graph is showing the fidelity, which is basically the quality of the quantum state over thousands and thousands of seconds. Just look at how flat that line is. A perfect memory would be a straight line right at the top, and this is ridiculously close. This proves that we can store quantum information for over an hour. That is way more than enough time to build these entanglement links across entire continents. So, the impossible problem now has a solution. The missing link has been found and built. So, what does this actually mean for us? What happens when this technology gets scaled up and we can start to entangle the entire planet? Wow, the applications are just staggering. We're talking about global communication networks that are literally unhackable. GPS systems so precise they could detect the tiny gravitational pull of a nearby mountain. We could link up quantum computers from all over the world to create one planet-sized supercomputer. You could access a quantum computer in the cloud from your phone. We could even link telescopes together to create an observatory the size of the Earth, letting us see the universe in ways we can't even dream of yet. You have to understand, this isn't just a faster internet. This is a fundamentally new way of manipulating information. We are literally tapping into the source code of reality itself to build our technology. This is a revolution that is just getting started, and it leaves us with this one final wild thought. We are building machines that can create spooky action at a distance whenever we want. So what does our world look like, and what becomes possible when we have a network that can entangle any 2 points on the entire planet?